All right, today we're going to talk about the power of logic, logical reasoning in physics and science. Now, I'm not going to give you a whole course on logic, but most of the logic we're going to use is very simple. So, for example, if somebody says that there are three statements, A, B, and C, and as a result of those, we can conclude D. The way we would write that as a logical sentence, what this means is A and B and C imply D. Now, to find errors in logical arguments, and I find them in physics papers all the time. For example, it might be that there is an unstated assumption here or some hidden assumption that the person didn't realize that they were making. So, for example, maybe it's not just that statements A, B, and C are needed to conclude D, but there is some additional statement or assumption E that has to come into play in order to make this true. So that is sometimes a way to catch a logical fallacy. Another one is, what if it turns out that statement C is actually the same thing as not A? So in other words, you figure out that actually what this argument says, this is the not sign. You have both A and not A in the same set of assumptions. Well, clearly, it can't be true that both A and not A, right? You can't say that the sky is blue and the sky is not blue. That can't be true, right? So often what you'll find is that arguments will contain internal inconsistencies or contradictions. But today, the sort of logic we're going to do is very, very simple logic. It's just something of the sort, for example, of let's say that statement A implies statement B. And what that means is every time that A is true, B must also be true. And then let's say that you discover that actually B is not true. B is false. So what do you think that says about A? If whenever A is true, B must be true, but B isn't true, then that must mean that A is not true. So very simple logic. So I want to talk about three of my favorite advances in science just based on logical reasoning. So today is about the power of logic in physics. Now in future seminars, I'll talk about where the logic went wrong, logical fallacies in physics that caused or continue to cause major problems in physics, such as Schrodinger's cat. A cat is both alive and not alive simultaneously, is a contradiction. It is a false statement. You would be amazed at the number of physicists who say that lie, that contradictory line that a cat is both alive and not alive simultaneously as a characterization of Schrodinger's cat. We'll get to that later. But today, I want to talk about some of the exciting discoveries that were made based on logical reasoning. So the first is this. This happened a long time ago, but it was one of the first examples of logical reasoning in physics that I remember. And it was this. How many stars are there in the universe? Is that number finite or is it infinite? Now, you remember from a previous seminar, infinity in the real world is actually false. It's actually a contradiction. It doesn't exist. But they didn't know that hundreds of years ago. So the question is the number of stars in the universe finite or is it infinite? Here's how they figured out that the answer is finite. Assume that the number of stars is infinite. What would follow from that? What would that imply if that were true? It would mean that here you are looking out in the sky. So you're looking in this direction, whatever direction it happens to be. Will you see a star? Yes. Because infinity is a big number, right? Because every direction you look, or at least, every single direction you look, you will be looking in the direction of a star. So there's a star there that's giving off radiation. Now, if you look in this direction, you also will see a star, and that star is going to be giving off radiation. And it turns out, because of our assumption that the number of stars in the universe is infinite, every possible direction that you can look upward always has light from a star coming toward your eyes. So what would that look like? Of course, when you actually look at the night sky, you can see a star there, a star there, but most of it is blackness, right? It's a dark sky. Most of it seems black. But if you were to get a photon of light from every possible direction you looked at in the sky, then what would you see at night? That's right. You wouldn't see night. There wouldn't be night at all. Every single direction would be as bright as the surface of a star, because every possible direction, no matter how small that angle is, every possible direction has light coming toward your eyes. And so it would look in every direction like there's nothing but light. There wouldn't be a night sky. Make sense? So assume the number of stars is infinite. That implies something like it is always bright in every direction. But what do we know? We know that that's not true. We know that there is nighttime and that it's sometimes dark and that you can look in certain directions where it's not bright at all. So what that means is this is false. So the falseness of this then applies that is false. And that's how we know that the number of stars in the universe is not infinite. Now, there's a little bit more to it than that, actually. You have to make some additional assumptions. It's called the dark night paradox. It has to, you have to assume the homogeneity of the universe. There's a lot of other assumptions that may be involved, but this is how it was taught to me. And it was beautiful because it clicked to me how logical reasoning can be used to figure out really interesting things about the universe. That's the first one. The second one that I'm going to tell you about is some nuclear physics for you. Now, it's going to be easy. I promise I will make this easy for you. And for you at home, I will teach this to a lay audience. But I think it's fascinating. First thing is, we are largely made of carbon. Not only is there a lot of carbon in our bodies, but a lot of scientists think that carbon is a prerequisite for life, something about the chemical properties of carbon. Now, carbon is an atom, but if you take away the electrons and you just have the nucleus, the most common type of carbon is called carbon-12. What that means is it has 12 nucleons. A nucleon is either a proton or a neutron. Half of those are protons, and the rest of those, the other half, are neutrons. Now, it turns out the atoms that make up our bodies all came from stars. It's called stellar nucleosynthesis, and it's just the idea that all of the larger elements in the universe actually came from the stars. Inside a star is almost exclusively two things. It's hydrogen, which consists of just a proton, usually, sometimes a proton and a neutron, and helium. Helium is 2 protons and 2 neutrons. So in a star, what happens is the hydrogen comes together to form helium. So how do you make carbon in a star? Well, you might say it's just a similar process. Helium nuclei come together to make the carbon nuclei. Helium has 2 protons, 2 neutrons. Carbon has 6 protons, 6 neutrons. So all you need is 3 helium nuclei to come together to make a carbon nucleus, right? Easy. But there's a catch. So to explain the catch, I'm going to draw something very simple. This is a curve of the binding energy per nucleon as a function of mass. Now, I told you I'd make this easy. So what this really means is this is a curve of stability of a nucleus as a function of its mass. All you need to, there's only a couple things that are really interesting about this curve. The first one is because this represents the region of highest stability, atoms or nuclei like to get to this point. So if you're really heavy, such as if you happen to be a uranium-235 nucleus, you really want to be here. So you'd prefer to divide up into smaller chunks and end up here. And that's what fission is. Nuclear fission is simply the breaking up of these nuclei into smaller, medium-sized nuclei and releasing energy. They get more stable. Well, you can do the same thing from over here. So this is the direction of fission. Now, what if you start with atoms or nuclei over in this region? Well, if they combine together, then they can get heavier and they can end up more stable, and that's where they want to be. That releases energy. So that process, when you go in this direction, is called fusion. And that's what happens in stars. Another thing that's interesting about this curve, in terms of the question that I'm asking, in terms of how do you combine 3 helium nuclei to make a carbon nucleus? Well, it turns out that this little thing right here, this peak, is a key element of this curve, because this is the helium-4 nucleus, which is this. And this right here is the carbon-12 nucleus, which is this. And there are little peaks right there. So carbon-12 is in fact more stable, or has more binding energy per nucleon, than the helium-4 nucleus. One way to do this process would be, let's bring 2 helium nuclei together first, and then add a 3rd helium nucleus. But when you do that, you end up getting an element called beryllium-8. So beryllium-8 has 4 protons and 4 neutrons, but it's extremely unstable. It is less stable per nucleon than the helium-4 nucleus. So it immediately decays. Well, very fast. In fact, the decay of beryllium-8 it has a half-life of 8.19 times 10 to the minus 17 seconds. What that means is, move this decimal place over 17 times, and that's how small this number is. It's a very, very, very brief time before beryllium decays back into 2 helium nuclei. So now, if you start with, so let's say you have a beryllium-8 nucleus. It has a very short half-life to decay. It's about to break into 2 helium nuclei, which are called alpha particles. But just in that time, that short time period, it happens to be hit with another helium nucleus. That's the idea, is that that would then create your carbon-12. But it releases so much energy that carbon-12 now has a huge amount of energy. It immediately wants to break back down into the 3 helium nuclei, or alpha particles. So that ends up being the problem, is that beryllium-8 lasts a really, really short time. And then even if you could combine those 3 helium nuclei to create the carbon-12 nucleus, there's so much additional energy in it, because it's such a favorable reaction, that all that energy goes into breaking itself back up into those 3 nuclei. So what ends up happening is, to make carbon-12, you start with 3 helium nuclei, add them together, you get carbon-12 and a whole lot of energy. But that energy has to go somewhere. And usually, that energy goes into breaking this back into the 3 helium nuclei, or the 3 alpha particles. In almost every situation, that should happen, which means that there really shouldn't be any carbon-12 in the sun at all, or anything bigger than carbon-12. In other words, stars should only have hydrogen and helium. And yet, we know that there is lots of carbon in the universe, and I know that because in order to make this video, I have to be alive, and that means requiring a lot of carbon for my body. So there was a British astronomer named Fred Hoyle, who basically made the following argument. He said, let's start with this notion. Let's start with assumption 1. All elements are created in stars. Now, it turned out that was his hypothesis. He's very famous for that hypothesis, and it's probably true. The second thing he noticed is that creating carbon-12 or anything higher, and when I say anything higher, I mean basically everything that we're made of, more or less, except for the hydrogen in our water, in our bodies, but the oxygen that we breathe, the nitrogen that we breathe, the phosphorus, all the different elements in our body, all of that stuff comes from the stars, and creating carbon-12 requires this 3 alpha reaction. And the alpha here, remember, is that helium-4 nucleus. The third thing he realized, without some means for the reaction energy to be released, the 3 alpha reaction will produce no carbon-12, or essentially no carbon-12, or anything higher. And then number 4, there is lots of carbon-12. So how do you explain this? What these say is that there shouldn't be any carbon-12 at all unless there's some means for the energy in the reaction to be released. Now, in nuclear physics, what we call this is a resonance. What it means is that there is an excited state of a nucleus that allows for the absorption of this energy, and eventually it will then radiate that energy away in the form of electromagnetic radiation. So in other words, what he really said was, without a resonance at the right energy, then that reaction won't produce any carbon. But, of course, we know that there is lots of carbon. So this is like the example before where we had A implies B. We realize that not B is true, and so that implies not A. So in this case, these things imply that there should be no carbon-12 at all, but there is lots of carbon-12. So what does it mean? It means that there must be a resonance at the right energy. Well, what's the right energy? The right energy means that the energy released by the reaction. So what is that energy? That energy, in going from helium-3 to carbon-12, is 7.275 millielectron volts. This is a measure of energy. You could call it joules, you could put it in any units, but this is a measure of energy. So the point is, this reaction produces this much energy. So here was the genius of Dr. Hoyle. He realized that according to everything we know, or everything we knew at the time, there shouldn't be any carbon in the universe. But that can't be right, because our ability to realize these things depends on our being alive, and our being alive depends on there being carbon, right? And we know that there's lots of carbon and higher elements in the universe. We know that. So that must mean there is something wrong with our understanding. There must be some place for that energy to go so that it can be released without the carbon breaking back up into those 3 alphas. Does that make sense? So in other words, what he did was he made this argument, this logical argument, and as a result, he realized there must be a resonance at this energy of carbon-12, or around there. It doesn't have to be right on it. So he predicted that. And as it turns out, it was not known before then, but as it turns out, there is indeed a resonance at 7.7 MeV, which isn't exactly the same, but is pretty close. And that's called the Hoyle state of carbon-12. So what ends up happening then, because there is this resonance at this energy of carbon-12, then instead of carbon-12 always immediately breaking down into 3 alpha particles, it sometimes just radiates a photon at this energy and stays as carbon-12. Now, it turns out it doesn't happen very often. Even when carbon-12 is made and it has this resonance frequency, it's still only about 1 in 2,400 cases does carbon-12 remain instead of decaying back down into those 3 alphas. But that's just enough to make enough carbon for the universe to have enough carbon for us to exist. Isn't that amazing? And what's also interesting, of course, remember in the previous talks, I talked about the fine-tuning argument, the Goldilocks enigma. Well, this is just yet another example of, if this resonance frequency didn't exist or was much further off than this, then that would have significantly reduced or eliminated the quantity of carbon-12 created by stars and could have prevented the possibility of carbon-based life forms at all. And it's possible that carbon is the only element that can be used in life formation. So this is just a really interesting example where an astronomer was able to figure out nuclear physics, something about nuclear physics, simply by making a logical argument of, well, it should not be possible to make carbon-12 in the sun unless there was some way for the carbon-12 to release that energy without breaking down into alphas. In other words, there had to have been a resonance energy, and there was. I think it was really amazing.